In this video, we are going to continue our look at linear second-order homogeneous differential equations with constant coefficients. In other words, differential equations which can be written as ay prime prime plus by prime plus cy equals 0, where a, b, and c are constants and a is non-zero. In the past two videos, we presented this idea of, okay, starting with this differential equation, write down what we call the characteristic or auxiliary equation, which looks like it's a quadratic expression, ar squared plus br plus c equals 0. What we want to do now is solve this quadratic equation. So find the roots of this quadratic expression on the left-hand side. From the quadratic formula, the roots look like negative b plus or minus the square root of b squared minus 4ac divided by 2a. In general, those are the roots. And in the last two videos, we imagined that the discriminant was greater than or equal to 0, so that we were looking at real roots. In this video and in the next, I want to look at roots which are not real. That means that we would be taking the square root of a negative number. So in particular, imagine that b squared minus 4ac was less than 0, so that when we take the square root, we're going to pick up an imaginary term in the numerator right here. We could just talk about what happens when the discriminant is less than 0. And in the next video, I'm going to give you basically that broad view. But for this first look at having not real roots, I want to focus on just one particular scenario, which is imagine that this discriminant is negative, so that we're going to pick up an imaginary term here, but that this leading term in the numerator, what we're calling negative b, is actually 0. So imagine, in order to be in the situation, that the discriminant is negative and b is 0. With that, what we can do is say that the roots are going to have one particular form. They're going to look like 0. So keep in mind here, this equals I'm doing is for this situation. It's not true in general. 0 plus or minus the square root of 0 squared minus 4ac divided by 2a. Okay, this 4 is a perfect square. The negative here is what's going to be making this product negative. So a and c are actually going to be, the product of a and c is going to be a positive number. So what I'm going to do is say that this is plus or minus. And then because of this negative here, I'm basically going to pull the negative 1 out. So just go ahead and take the square root of negative 1. That's what we call this imaginary number I. I could also go ahead and pull the 4 out. So take the square root of 4, we get 2. That's going to cancel with the 2 in the denominator. So that what we're left with is the square root of AC divided by A. If you're looking at that and you're wanting to do a little bit more with the A's, you can do that. But I'm going to stop it here because I've taken it as far as I wanted to. What we are looking at in this situation, where the discriminant is negative and b is 0, is what is called a complex conjugate pair of imaginary roots. Complex conjugate means they just differ by a sign here in front of the imaginary component. So we have I times this fraction and negative I times the same fraction. This number today we are going to call beta. Now that we've written this as beta, we can say that the roots in this situation have the form plus or minus I times beta. Okay, what we are going to do is take the approach of the situation where we had distinct roots and use these expressions in those exponential functions to arrive ultimately at the type of linear combination that we would like to say solves this differential equation for this scenario. And then we will do an example. If the roots to the characteristic equation have the form I beta and negative I beta, so plus minus I times beta, then according to the theory that we've already seen, we should be able to write down a general solution that looks like a linear combination of two exponential functions. So here I've written d1 times e to the I beta x plus d2 e to the negative I beta x. So there, I beta and negative I beta are the solution or the roots to the characteristic equation. That follows what we've done in previous lectures. And this does solve the differential equation, but what we would like is a presentation which is real, so that when we look at it, we're not like, oh, it's complex numbers or anything like that. So I'm going to show you how to get there, and it's going to involve Euler's formula. I have a video on Euler's formula if you'd like to review that, or you can just trust that I'm about to do the right thing. So let me take these complex exponentials and replace them with combinations of cosine and sine. That's what Euler's formula allows us to do. So this first piece, I'm going to leave the d1 out front. E to the I beta x can be written in terms of trig functions as cosine beta x plus I sine beta x. So that is a way to replace that complex exponential according to Euler's formula. So that this is Euler's formula. Okay, we're not done because we also have d2 times, now I'm going to do the exact same thing, but we have negative I beta x. So that's going to be like cosine of negative beta x plus I times sine of negative beta x, like that. Okay. The first piece looks great already. The second piece, we have this negative in front of the angles that we're plugging into the cosine and sine function. What we're going to use here are symmetry properties of these two functions. Cosine is even, whereas sine is odd. Even functions have the property that if you plug x or negative x into the function, you get the same thing. So cosine of negative beta x is the same thing as cosine of beta x. Actually, let me just write that here rather than rewriting all this and just making some little changes. I'm just going to say, hey, since this is even, cosine of negative beta x is cosine of beta x. Whereas for an odd function like sine, if you plug in x, you get negative plugging in negative x. I didn't say that very well. If it's odd, that means that f of negative x equals negative f of x. Okay, that's the general way to describe an odd function. So when we realize that sine is odd, what that means is that sine of negative beta x can be rewritten as negative sine beta x, negative 1 times sine of beta x. So on the next line, I'm going to start doing some combinations. When I get to, oops, sorry, and grab that. When I get to this, cosine negative beta x will replace that with cosine beta x. And here, sine of negative beta x will become negative sine of beta x. Okay. Now this is ideal because I have the same looking cosine functions in both of these expressions as well as sine. So I'm going to be able to combine them together. Let's combine like terms here. I'm going to pair these up and pair these up. Notice the cosine parts are real looking. We don't have an I coefficient, and we do in front of the sines too. So that's another way to think of this as combining like terms. All right, so on the next line, what I'm going to do is recognize that we have d1 times the cosine plus d2 times the same cosine. Let's write that as d1 plus d2 times cosine of beta x. Then similarly, looking at the sine functions, we have I d1 and then negative I d2. What I'm going to write is the I out front and then d1 minus d2. And then sine of beta x. Okay. Just to recap where we are so far, we had a second order linear differential equation, and we said that the roots to the characteristic equation had the form plus minus beta I. So we wrote down a linear combination of exponential functions. And if you take that linear combination that we started with and plug it into the left-hand side of the differential equation and simplify, you will eventually get to 0. This is a solution. It's just a solution that has some imaginary components in it. Likewise, this is a solution. In fact, it's the same thing as that. It just looks different we've written it differently by using Euler's formula. However, what we would like to see are two solutions that look like real recognizable functions, and we want to take a linear combination of them and have everything just look real. So here is essentially a trick to get to that. I would like to take d1 plus d2 and just say, could this be thought of as a real number c1? And likewise, could it be the case that I times the quantity d1 minus d2 could be presented as a real number c2? So that what I would be looking at is a real number times cosine beta x, beta is a real number, so this would be a real number times just a function of a real angle, plus a real number times sine of beta x. That's the dream. Okay. And there is a way to do this. So this basically gives us a condition on how to pick d1 and d2 so that they can be presented in this way. Here's how we're going to do it. What we will say is, let's let d1 be c1 minus ic2 divided by 2. So d1 is a complex number here. It has the form c1 minus ic2 divided by 2, where c1 and c2 are just random real numbers. On the other hand, d2 will be c1 plus ic2 divided by 2. It's a nice little exercise with complex numbers to see that this is the correct way to choose d1 and d2. So why don't we pause for a second and see what happens if you take d1 and d2 the way that I've written them here, add them together. Does this simplify to just the real number c1? And then what happens if you take d1 minus d2 and then scale it or multiply it by the number I? Do we end up with just a real number that we've named c2? And then I will come back and finish the computation. Okay, let's check how you did. So if I take these numbers the way that we've written them and do d1 plus d2, I'm just going to do that to the right here, d1 plus d2, that's going to be c1 divided by 2. I'm just going to write these out as individual terms. So c1 divided by 2 minus I c2 divided by 2 plus c1 divided by 2 plus I c2 divided by 2. Okay, you see a couple things. Why we had the complex parts change sign. Now this cancels with that. And then you also see why we divided by 2. So I end up with c1 divided by 2 plus c1 divided by 2. And that does give us a coefficient, which we're calling a real number c1. On the other hand, what is I times d1 minus d2? That's going to be I times c1 over 2 minus I c2 over 2 minus c1 over 2 minus I c2 over 2. Okay, like that. This time, the subtraction here calls the real parts to cancel. So the c1 terms go away, and we are left with negative, inside the parentheses, negative I c2 over 2 minus I c2 over 2, so that overall, this is I from out front times negative I c2. Negative I times I is negative 1 times I squared. I squared is negative 1, so this is negative 1. So positive 1 is what I'm trying to get to. So this is overall C2. Let me just make a little note here what I just did out loud. This coefficient in front of the C2 is like negative I squared, but that's like negative 1. Okay, so that's what I was trying to say out loud. All right, so we started off with an expression that looked very complex, literally. So we have these complex exponentials. We then used Euler's formula to write them as linear combinations of cosine and sine, but we have these complex looking coefficients in front of them, and we wanted to get to a solution that we could present as a linear combination of functions of real numbers. So at the end of the day, what we have, if I can squeeze it down here, is kind of a way in the background to choose numbers. So maybe I'll just say, let's leave this aside. We can now say that the general solution can be written as a linear combination of cosine and sine, where it looks like just a real number c1 times cosine of beta x plus a real number c2 times sine of beta x. Okay, so through all this work here, we just did the algebra to get to this linear combination of cosine and sine, where here c1 and c2 are real numbers. This is giving us a solution like we had before, particularly when we looked at the situation of having real and distinct roots. Here we have distinct roots, I beta and negative I beta. So we have distinct roots, but they just happen to be imaginary. So instead of exponential functions, we ended up with these trigonometric functions. Okay, given that this is the general solution to such an equation, let me now show you an example. In case you're feeling a little uncertain about what beta actually is here, I think when we work through the numbers with a real example, you will be able to recognize, oh, that's what beta is. Then we can write down this presentation for a specific equation, and then we will solve an initial value problem. Let's look at this example, y prime prime plus 4y equals 0. We do have initial conditions, but we will worry about those after we found the general solution. Looking at this second order equation, notice it's like missing the first order term. There is no y prime on the left-hand side, and that should make sense because our conditions for having pure imaginary roots, let me just remind you. We said that we wanted the discriminant b squared minus 4ac to be less than 0. But also, to get pure imaginary roots, the b term that goes with the first order derivative, so the plus by prime, the b coefficient is 0. So if you don't see that first order term, that's a clue that you might be looking at a situation where you have pure imaginary roots. You could even take this a little further and say, well, hey, if b equals 0, then this is going to go away. So really, this condition just becomes negative 4ac is less than 0. And you could even say a little bit more about that, which is like if b is non-zero, so that this is the discriminant, this is going to be negative whenever a and c have the same sign, so either both positive or both negative. Since it's the homogeneous problem and you could divide everything by -1, it's essentially like a and c are both positive. That's what we're looking at here. So a is 1 and c is 4, b is 0, so that we have a negative discriminant and no middle term b. All right, I just said a lot, but really all we needed to do was pass immediately to the characteristic equation. So all this was just kind of an aside. What are the roots to this? Well, the characteristic equation is r squared plus 4 equals 0. Be really careful here not to write r squared plus 4r. It's tempting, but we are missing the first order term. So the only things that we should see in the characteristic equation are quadratic and constant. Okay, what does this tell us? It tells us that r squared is -2. -4, kind of jumped ahead of myself there. So r squared is -4. That means that r is plus or minus square root of -4, but that is plus or minus 2i, where I is the imaginary number. You could have also gotten to that from the quadratic formula if you wanted to. The roots, you could always find that way, but here it's kind of easy to isolate r. When I kept referring to beta before, beta is this number 2. So here, plus minus beta I is like plus minus 2i. So what we called beta is going to get called 2 in this example. That means now that we've identified beta, we're ready to write down the general solution. So our general solution to this second order equation is going to have the form y of x equals a constant times cosine 2x plus a constant times sine of 2x. And that's it. So with these equations, the main work is identifying what kind of roots you have. And then once you have the roots, recognizing the general form to write down. So there's not a lot of work to do from here to here. You just have to make sure that you get the roots correctly and then make sure that you use the correct general form. Okay, this is the general solution without any initial conditions, but we do have initial conditions on y and y prime that will allow us to solve for actual values for C1 and C2. So what I would like for you to do is pause and see if you can write down what these initial conditions are telling us. So you should end up with two equations for the two unknowns at C1 and C2. And then I will come back and finish the computation. All right, our initial conditions tell us that when the independent variable x is 0, y is 1, and y prime is -2. So what we're going to do is substitute those values into our general solution so that we can solve for C1 and C2. What I'm going to do now is take x and replace it with 0. And then I know that when x is 0, y itself is 1. So let me write that up here. 1 equals C1 times cosine of 0. You got to know your cosine and sine values here. So cosine of 0 is 1. And then sine of 0 is 0. So immediately we know that C1, this first constant, is just 1. Okay, that's good. Now to use the second condition, I'm going to differentiate the general solution to write down an equation for y prime, and then we'll substitute into that. So y prime is going to be, with the chain rule, -2 times C1 times sine of 2x. I'm going to go ahead and use the fact that C1 is known to be 1 to write -2 sine of 2x. And then when we differentiate this, it will be 2c2 cosine 2x. Okay. Plug in x equals 0 on the right, -2 on the left, and we have -2 equals sine of 0 once again is 0. Cosine of 0 is 1, so this is 2c2. So this was a pretty nice system to solve. We can look at this and say c2 is -1. All right, so while this was the general solution to this differential equation, for the initial value problem, we found that y of x is 1 times cosine of 2x minus 1 times sine of 2x. Okay, so that wraps up this discussion of the situation where the roots to the characteristic equation are pure and imaginary. In the next video, we will look at the situation where this discriminant is negative, but the b coefficient is not 0. That's going to give us what we call complex conjugate roots.